Hi everybody, this is Mr. Folly, and welcome to our first lecture on Unit 8 Solutions. Yay! Okay, so a touch of this is review, but it's still very, very pertinent to what we're doing. So let's take a look. A solution is a homogeneous mixture of a solid and a liquid, a solid and a liquid, gas and a liquid, or gas and a gas. I can use my commas. Solid and a liquid, comma, gas and a liquid, comma, or gas and a gas. So that's it. So remember, homogeneous means that the samples are the same. All right. The solute is the smaller part of the solution. So if I have salt water, it would be the salt in salt water. When we breathe, remember, oxygen is 20% of the atmosphere, and nitrogen is 80% of the atmosphere. So oxygen would be the solute in the atmosphere. The solvent is the bigger, usually biggest part of the solution because you can have more than one solute. Water and Pepsi, water and Kool-Aid, and most of what we're going to deal with is going to be water, solids and water, so that's okay. All right, concentration. So review. Remember, moles equals MV. You'll also see every now and then molarity. Whoa, that doesn't even look like an M. Molarity equals moles over liters. Big M is molarity, and then it's called molar, which is big M. V is volume. The entire solution means solute and solvent in liters, and moles is moles. Dilutions change the concentration to a lesser desired amount. When you do a dilution, the number of moles is constant, but the total volume changes. So if you're looking at this dude right here, and little baby Chucky it, I got 1, 2, 3, 4, 5, 6. I have 6 particles. And then I add more water, and I have 1, 2, 3, 4, 5, 6 particles, right? So it's still going to be 6 moles and 6 moles, but this one is concentrated, and this one is dilute. The equation for it is M1V1 equals M2V2. 1s are befores, 2s are afters. So let's do a sample problem. How do you make 30 milliliters of 0.5 molar NaCl solution given a stock solution of 6 molar? A stock solution, so you'll see this a lot. A stock solution is an unlimited amount of concentrated solution. Really, it's not unlimited, but if you think about something being in stock, that means they have all you need for it. So let's take a look at this. All right, so M1, original molarity. V1, original volume. M2, molarity the other one. V2 is what we're going to have left over, right? Well, is going to be the amount we need. Okay, so I need 2.5 milliliters, and what we're going to do to say this is take 2.5 milliliters of concentrated solution and add enough distilled water to make 30 milliliters of solution. Okay, so remember, we want to make 30. We're going to take our answer of concentrated solution and add enough distilled water to make 30 milliliters of solution. So this is weird. You have to say add enough distilled water because it doesn't exactly add up. So if I had a little beaker of 10 milliliters of NaCl and I added it to 20 milliliters of H2O, you'd think it would add up to be 30. It doesn't. It's a little bit less because it fits in the spaces in between. Okay, so that's why you've got to say this annoying thing. All right, describe how to make 50 milliliters of 2 molar KCl from a 10 molar stock solution. I didn't leave myself much room. I'll do it over here. So M1V1 equals M2V2. So 2 times 50 equals 10 times V2. I'll bust out my calculator here. So 2 times 50 is 100. I guess I really didn't need that. V2 is 10. I got all that. 10 milliliters. So then describe how to make it. Take, oops. Ooh. I touched something on my computer I didn't like. Okay, so we're going to type this because my computer's being weird. We're going to take 10 milliliters of concentrated, I'm not going to say concentrated, I'm going to say 10 molar here, 10.0 molar solution, and add enough distilled H2O to make 50 milliliters. Okay? I just don't want to ruin my little spacing thing here. So 50 milliliters. Well, let's see if I can back this up. Yeah, I can. All right. Dissolving equations. So ionic solutions, again, we're focused on the ion part of ionic solutions. So ionic solutions turn into ions when they dissolve. Remember, ionic compounds will always start with a metal or NH4. Quick little metal review here. Here's your periodic table. We got that magical line here. All of these guys are metals, not hydrogen. Okay. It is true that these down here are metals as well. All right. So what's going to happen is ionic solutions turn into ions. So we've got to remember our ions, both the ones from the periodic table and the ones we had to memorize. So KCl is made of the K positive ion and the Cl negative ion. That's it. AlF3 is made of the Al plus 3 ion and the F minus 1 ion, but we need to balance it, right? So balance. So you see how here I have 1K, 1K, 1Cl, 1Cl. Over here I have 1 aluminum, 3 fluorines. That's why I need a 3. Okay. Also, when we're dissolving this, when these dissolve, we're going to have, it's going to split into 2 pieces. This is my positive ion. Let's see if I can make this obscenely bright. I thought I had a bright yellow. I guess not. This is positive. So notice the negative end of water, the chin of Mickey Mouse is attracted to it. Actually, I go very dark with this one. And this one right here would be negative, so the ears of Mickey Mouse are attracted to it. So you're going to be asked to draw a picture of it, or a picture as they say in Indiana. And if I have a positive thing, remember, water is polar, and it has a negative end at the chin of Mickey Mouse and positive ends at the ears. So make sure if it's positive, the negative is pointing to it. Now, covalent, called molecular solutions, do not turn into ions when they dissolve. Covalent will start with nonmetals and be polar. So when we do this, notice we have no ions. All that happens is your substance just turns into aqueous and it's surrounded by water. Okay? Water will not pull apart the molecules, but it will still like it. So see how this end, I made my little electron cloud for the molecule here. This end is a little bit positive, so the negative oxygens, the chins of Mickey Mouse, are attracted to it. Okay. This end is a little bit negative because it has the extra electrons, see the bigger cloud, so the positive hydrogen goes with it. All right. So solution-like mixtures, gases dissolve in other gases, and solids can dissolve in other solids, and this is a special type of solution called an alloy. All right. Molarity of ions is determined by the coefficients of the dissolving equation. Okay. So if I have 3 molar solutions of Na2S and AlBr, which one will have the greatest molarity? So I'm going to start by writing the dissolving equation of Na2S. Na2S is going to be Na positive plus S negative 2, but boom, I've got to balance it to get my 2's for each spot. So on this one, if I have 3 molar Na2S, it's going to turn into, got to double it, 6 molar Na positive. And notice this is the same coefficient, 1 and 1, and 3 molar S negative 2. So let's take a look at AlBr3. You probably can already see the answer. So aluminum is plus 3, turn into its ions, and bromine is minus 1, but I need 3 of them. And again, these charges come from the periodic table. Look at the columns of the periodic table, and they'll tell you. So that means if I have 3 molar AlBr3, I'm going to have the same molarity of aluminum, same coefficients, and I'm going to have 3 times. 3 times 3 is 9. 9 molar Br negative. So which ion has the greatest molarity? 9 molar Br negative. Gases are always molecular and are quite soluble in water. Warmer solutions dissolve less gas. Colder solutions dissolve more gas. I think of that as they swirl, woo, and only when it reaches the surface can it go, I'm free, I'm free. So because warmer solutions, the particles move more and more exposed to the surface, more will evaporate. Or dissolving means it will effervesce and leave. So, gases can make solutions with each other. A gas in a gas is almost always homogeneous. And we are done.